All right, so today we are lucky to have Andrew Miller, who's going to tell us about Ethereum. Isn't Turing complete? Doesn't matter anyway. This meetup is being co-sponsored by the guys at IC3 at Cornell. I thank them for letting us squat on your invitation to Andrew, as well as BitDevs. BitDevs is a community of developers in New York. We get together regularly to discuss what happens on Bitcoin. We have a Socratic-style meetup coming Tuesday. Yeah. And after that, we're going to have, at the end of August, a debate about hard forks. So you guys are all welcome to attend.
And immutability.
And immutability. I posted this under the banner of our White Paper Wednesday. So this is a journal club. If you have a topic you want to dig into, come to me and we'll figure out appropriate literature for it, and we'll all read it and get together and discuss it. So Andrew, I pointed everyone to your Hawk paper, so chances are good a few people here will have read it and ask good questions. With that, I'll turn it over to Jim. Where do you go? Jim, who wants to say a few words?
Thanks very much, Bob. I'm Jim Dellingle, Executive Director of IC3, which is the initiative for cryptocurrencies and contracts. I want to thank the BitDev guys, Jay, Max, and especially Bob for all the work they did promoting this event. Give them a hand, please. Also want to thank them for connecting us with Microsoft, who provided this beautiful space. Give Microsoft a hand, please. So just a few words about IC3. IC3 is a group of 11 professors, their students, and currently 4 partners in industry that are dedicated to taking all the hype we know about blockchains and smart contracts today and taking all that which is scientifically feasible and useful and transforming that into reality. We have deep expertise in cryptography, distributed systems, game theory, programming languages, and system security techniques. And we're applying that currently to over a dozen very practical projects that are addressing some of the looming questions and obstacles to reach that reality I mentioned just a moment ago. With us today, we are delighted to have Professor Andrew Miller. But before I introduce Andrew, I just want to quickly introduce Professor Ari Jules, who is co-founder and co-director of IC3. Ari, you want to just wave to the crowd? So you know who Ari is now, and you can see him afterwards. Ari has many notable contributions to this field, not the least of which is he bought the pizza for tonight. So, so why are we doing this? Well, we are educators. But that's not really why we're doing this. We're doing this to raise awareness about IC3, and my job really is to help IC3 get well funded. We are seeking partners who have a substantial stake in the future of blockchains and smart contracts, and would like you to partner with us. And we have 4 partners so far, 2 announced, 2 will be announced shortly, and we hope to see many more. So if you share our vision for ubiquitous smart contracts that are performant, reliable in all respects, please see us afterwards and we'll tell you about how you can collaborate with us further. Okay, so that's my spiel. Now I'll introduce Professor Andrew Miller. Andrew Miller just received his PhD from the University of Maryland. He did that with Elaine Shee, who is also a co-director of IC3. Andrew is, as you'll see, extremely talented. We're delighted to have him here. We normally want to do these meetups at Cornell Tech, which is temporarily in the Google building, another behemoth of the industry. But we're bursting at the seams there, so it wasn't possible. Really glad Andrew was in town. We wanted to get him out here in front of you guys before he takes off for the University of Illinois Urbana Champaign, where he's going to be a professor. So, Andrew, please come up and educate us.
All right, thank you.
Please give Andrew a hand.
All right, hi everyone. You can hear me good, right? Everyone else can hear me all right? Okay, thank you all for coming out. Especially thank you BitDevs folks and Bob and York Roads for merging this event and making it a bit bigger and helping us get this building. I'm going to talk about a couple of things. I'm going to start by, this is the red herring of Turing completeness, because I'm going to start by talking about kind of a rant about what we should and shouldn't say about Turing completeness. I'm going to skip my usual intro slides because I'll assume we all know what blockchains and Ethereum are. So digital currencies run on a decentralized blockchain, but it's not just currency because we can also do things where we have smart contracts, which are general purpose programs that run on top of this. Just for a little bit of context, I just got back from this IC3 boot camp and workshop, kind of like an extended hackathon, and it was awesome. We had Ethereum Foundation engineers there, as well as all the really bright students at Cornell and visiting students who are staying at Cornell for a while, plus several industry folks. And we basically took about 5 or 6 projects from start to completion, and these were super ambitious, more ambitious than you'd find in an ordinary hackathon. They involved advanced cryptography and zero-knowledge proofs and trusted hardware platforms and all of this. And all of this is possible because we're building on top of this exciting general purpose platform. And so I came up with this rant. I decided what I want to talk about because I figured that would be a good opportunity to practice venting about my reaction to this sort of argument. So I wanted to pick, people often make bad arguments using Turing completeness or facts about Turing machines as the basis of their argument, and they usually don't hold. And this is one representative example on RBTC, the best subreddit, but it's representative. So the message here is that because Ethereum has a Turing complete smart contract language, that's a terrible choice for a smart contract language. And the reason why is because of the halting problem. We know that Turing machine programs are undecidable, which means we can't tell for sure if they're going to halt or not. So before I turn into this argument, what are Turing machines? Turing machines are the little simple computational model where you go left and right and you can set bits. This is the Hello World program in Brainfuck, the language of Turing machines. So if you've seen this, it's a horrible language, and Turing machines are a total pain to work with. They're not fun to work with. The reason why Turing machines are so essential in computing theory is because, to kind of a more or less degree, it doesn't matter which exact computing model you use, they're all kind of equivalent. And so this is in the sense that if you have something that's not exactly a Turing machine, you can probably build a Turing machine in it. And likewise, even if you can do it the hard way with that awful language, you can implement other things in Turing machines, so they can all simulate each other. This comes with a couple of caveats. So the first one is that the original statement of this doesn't say anything about efficiency. You might be able to do this simulation, but it might be really inefficient. What you can say is that this is efficient with only some kind of theoretically polynomially asymptotic overhead. So you can simulate one machine with another without too much overhead, but this is really a theoretical claim. So when you're looking at whether a computing model is efficient or not, the details like the actual instructions actually matter. The other caveat, which I'm going to go into a little later, is that this is a universality statement for computable functions, which are programs that take in some input and give some output. But looking ahead, that isn't the only thing that smart contract systems do. You don't just simply compute something and want to get an output. We have interactive systems where you want to compute and have some kind of side effect on some other system, like moving money in a blockchain. And there's no guarantee that computable functions represent everything that you would want to do in a larger system. So the halting problem, this is the Wikipedia definition of the halting problem. All right, and so it's about the fact that if you take an arbitrary Turing machine program, you can't guarantee that for all arbitrary programs that you'll be able to tell whether it finishes or not. So coming back to this argument that I want to pick apart. Well, the first way to pick it apart is that Ethereum isn't actually Turing complete. This is the pretty simple statement, right? Since Ethereum has gas, when you send a transaction to a contract, you know exactly some bound on how long it's going to run for. That's enough to make it not Turing complete. So that fulfills the portion of my talk title, and it breaks that argument, but that's totally boring. I'm not going to talk for an hour about that way in which it's not Turing complete. The real reason I wanted to pick apart this argument is because, right, this just is not a correct application of logic. All right, the fact that you can't tell whether any possible smart contract program, like you look on the blockchain, you see an arbitrary bytecode smart contract. Yeah, you might not be able to tell whether with infinite gas whether it would finish or not. But that doesn't mean that we have to be willing to use all arbitrary smart contracts. So for most smart contracts, you can tell whether they decide or not, and you get to choose which smart contracts you're going to interact with on Ethereum. So it's easy for you to say, well, I'm only going to interact with the contracts that I have seen the program code for. I have seen the annotation, or I've understood it well enough to know when or it won't take some particular action or not. So there's no reason why you have to have a smart contract programming model that makes it so that every smart contract that's on there is easy or safe to use because users can exercise some kind of discretion or ask for some extra proof on top to know what it's going to do. All right, now, in this general sense, there may be some programs that we can't tell what we're going to do, but in general, the programs that we care about don't have this quality of not being able to tell what they're going to do or whether they're going to end or not. I think the deeper point here is that I see the halting problem in these things about Turing machines often brought up to serve as some kind of excuse against using formal analysis. This is using logical tools that allow you to get some kind of logical guarantee that a program is going to satisfy some property or not exceed some invariant or not leak all the money into a black hole. All right, and you can apply formal analysis tools to ordinary Turing-complete programming languages like C. So actually at our boot camp and retreat that I told you about, we had a really interesting talk from Christian Reitweissner, who's the Solidity compiler developer from Ethereum. And he showed us this tool that's really cool, which is a compiler from his Solidity language into this formal analysis tool called Y3, which is built in the Coq theorem proving system. And it allows you to then take a model of this Solidity program code and go through this theorem prover and prove facts about what the program does. And if the program doesn't satisfy one of the invariants, the point of Y3 is that it helps you understand why the invariant isn't satisfied. So you can still use formal analysis tools even if you use a C-like language. All right. Now, going back to this notion of Turing machines are universal because they're universal for computable functions. This is kind of a tautology, but you never need an actual Turing-complete language if you want to be able to solve practical problems that you care about. So I can make this statement, which is that there's no efficiently solvable problem that requires a full Turing-complete language. And really unpacking this, it's just a tautology, because when we say efficiently solvable in computer science, what we mean is that if you take the size of inputs as a number n, then you look at how long a program runs as a function of that n, then a problem is efficiently solvable if there is some polynomial time that bounds how long it takes some Turing machine to compute that function. So by definition, you could take that polynomial time, use that as like your gas limit for how long you would want the program to run, and you'd be able to implement it that way. So that was a couple of the angles of this. So Ethereum's not Turing complete, but you don't need Turing complete for computable functions. Let me go on a bit. Even if you had a Turing complete language, it wouldn't be universal for to have as a smart contract in a blockchain system. So to illustrate this, I want to tell you about the new Ethereum alternative that I'm introducing today. This is called Ethereum, and it is a Turing-complete yet utterly useless smart contract programming system. So this has most of the opcodes from Ethereum that you know and love. You can create contracts. It's got add and multiply. You can pop onto a stack. You can load from memory. It's got jump and conditional jump, so it's Turing complete. And it's got gas, so you know it's not Turing complete. The only thing it doesn't have is call. All right, so what would a smart contract system look like if you don't have call in your EVM? So call is the instruction in the EVM that lets you send messages from one contract to another contract. It's also the only instruction that lets one contract send money anywhere else. So if you create an Ethereum contract and you send it some neither, then it's gone into a black hole immediately. It'll never be able to get sent again. But it's still Turing complete, because you can still send messages to the contract, and it can do arbitrary Turing complete computations on it, especially if we don't enforce gas. And you can see those results written into a log or written into the persistent storage, but the money's stuck. So this is just to say that what we want in a smart contract system, and what the role of smart contracts in the EVM is to have these effects on the rest of the currency system, like the thing that keeps track of how much ether there is. And so even if you have, you can't compute your way out of this problem. If the instruction set isn't bound in a correct way to the other parts of the system that you care about, it doesn't help you to be able to compute functions with it. Computing functions with the system isn't the goal. You really care about having its side effects on the rest of the system. To kind of push this example a little further, there are ways in which Ethereum is more flexible than Bitcoin, and some of these ways have nothing to do with the Turing completeness of its programming language. So the point that I'm going to make is that because of Bitcoin's UTXO structure, even though if Bitcoin has some kind of smart contract scripting language in it, there's some things you can do in Ethereum easily that you can't do, or at least I don't know how to do with Bitcoin, that have nothing to do with the expressive, or they don't have anything to do with the Turing completeness of the language. So the best paper award at our top security conference, Oakland, a couple years ago was one of these fair lottery games built on the Bitcoin scripting language. So the fair lottery is when you have n players, they each put in a Bitcoin, they do some kind of cryptography exchanging thing, and then at the end of it they all walk away with some money. One of them walks away with all n of the coins and everyone else walks away with nothing, and it should be provably fair, so no one can get any advantage on any of the others, even if it's like n-1 of the people are colluding. Now the trick is that this lottery requires a huge amount of collateral. So if there are n people and each one of them is supposed to put in 1 Bitcoin, each party actually has to put in n squared amount of Bitcoin, which is huge. So it's n cubed in total amount of collateral needed when the total size of the lottery is only supposed to be n. Now, without going into too much detail, the way that this works is one of these complicated transaction scripts, and it involves doing the kind of thing that you know from the lightning circuits, where you sort of interact ahead of time with all the different pairs of parties and exchange these partially signed transactions that aren't valid till some other information's disclosed, and it uses time locks. I won't get into too much of how it works, or really any more about how it works, but the point is that because of the structure of this, it comes down to this one part where there's a single round where every party has to reveal their information, and anyone that doesn't has to refund everyone else. And because this all takes place in one blockchain round, like it takes place on one transaction that's committed or not, that's why you have to have this huge amount of collateral. What you can do with Ethereum that's really simple, and I don't see any way that you can do this on top of Bitcoin structures, you can make a lottery that doesn't require any additional collateral. So it improves on the amount of collateral required by a factor of n squared. You only need, all each party has to put in is 1 coin, and that's it, and the lottery is still fair. And it works by having a sort of tournament bracket. So what you have is pairs of parties at a time match off with each other, and what they do is commit to a random string by placing the hash of it on the blockchain. And then there's some time after which both commitments are received, and then the parties have to reveal what their commitment was, and then you XOR the two strings together to see who's going to win. And if you fail to put in your commitment opening by the end of this time limit, then you forfeit and the other party goes ahead to the next round. And so you do this like tournament rounds. It takes log n steps, and then at the end you're still going to have one party that has the same chance that he would have getting n amount, regardless of how many other players are corrupt, and you don't have to put in any of this extra amount of collateral. All right, and this is something that I am pretty sure that it's not possible to do on top of Bitcoin. One of my colleagues at Obentov is working on trying to do a proof to guarantee that it's not possible with Bitcoin, but at the minimum it's extremely complicated to even imagine how you might do it, and I'm pretty sure you can't do it, whereas it's very simple and direct in Ethereum. The critical thing that makes you do this, again, isn't the Turing completeness, but it's the fact that in Ethereum you can have persistent state where you have some code. That code can modify some state that then affects how a later transaction is processed. And in Bitcoin, because of the UTXO structure, you can't have a transaction script that places any constraint on what happens to the Bitcoins after a transaction passing that script is run. Like every transaction is inherently one shot. So what I want to do next is this is going to be the hardest technical part of this. I want to try to convince you with a kind of contrived example of another way that Ethereum is already not only not Turing complete, but it's not universal in the sense that you can pose a kind of game structure where you would like to be able to write a smart contract that does something, but you just can't do it, and it's because of a limitation of Ethereum's expressiveness. So this is going to be pretty complicated, so let me try to explain what's going on here. This is a game that, so imagine that the jigsaw scary guy on a trike tells you that he's got this proposition for you. The key thing here is that, I don't know if this laser pointer comes out, but the key entry point here is this double my money function. And just assume that Alice and the jigsaw characters have their public keys fixed in here. So what we want is for Alice to call this double my money function. And nothing's going to happen unless she deposits 1 million Bitcoins, million Ether, whatever, when she does so. And she has to, this only matters if she does it before some time b. Now, if she puts in that amount of money, and if the switch statement is true, which it starts off as true, then it's going to set her balance to be doubled. And then later on, after that critical block, she can withdraw whatever her balance is. So if Alice calls double my money before the deadline B, and all the conditions are right, then when she calls withdraw, she'll be able to get double her money back. So what's the catch here? Well, clearly it has to do with this tricky function, which Jigsaw can call at any time. And if he's a miner, he could just put this transaction in a block wherever he wants. And this sets the switch back to 0. So what happens is that it's OK for Alice to call double my money, but only if switch hasn't been set to 0 by the time her transaction's processed. So think about this as a puzzle, and I'll tell you what maybe some of the answers are in a moment. What you should be thinking towards is how can Alice not just interact with this contract directly by sending it a transaction message, but how could she create a smart contract for herself that does something like checks the value of switch like a guard, and then only triggers this contract if it checks that switch is okay. Right? That's what you should be thinking towards. But this is really carefully designed to be a good trap, so there's no way to do this in Ethereum. What you want to be able to do is to check whether switch is set, but since switch is a private method with no accessor function, there's no way programmatically to go ask the contract what's the value of switch at any given time. You might think of doing something indirect, like you try running double my money, and then you try to check if it's had the effect that you want, like you try to check if balance has been updated, and then just cancel the transaction with an exception if it hasn't. But you can't do that either, because it doesn't send the money directly. The only thing that this method changes is the state of balance, and balance is also a private thing, so you can't observe that directly. There's nothing that you can observe about this contract from within the EVM that would allow you to tell whether or not switch is 1 or 0, or whether this function's been run correctly. Another tricky thing you might try to do is to say, well, I can make a contract that only runs this transaction on a particular block, and I can even check the previous block hash and make sure it's the previous block hash I have in mind, and I can try to guarantee that my transaction is the first transaction in that block. And so if I know the previous block it ended with switch being 1, and my transaction's the first in the block, then that would be okay. But there's no way in Ethereum to guarantee that your transaction's the first one in the block. Now, the thing that I would have in mind to try to fix this, you might even try to do this more indirect thing where I somehow use Merkle trees, or I accept a Merkle tree proof as evidence so that I can maybe look at what's the current state of the EVM right before my transaction's running. And if in this state, I would look at the branch of the tree down towards this contract, and if I could check that then it has that value, then it might be safe. All right, but here you can't even do that, because even though you can load the previous block and maybe do something to try to understand the structure of the previous block, there's no instruction that lets you load in the hash of the current state. All right, so what I'm going to claim is that this trap is indeed dangerous. There's no safe way for Alice to submit a transaction to get past it. If you can think of one, let me know. And I'll tell you, there are two caveats. One is that this is what Vitalik came up with when I told him this puzzle. He said, well, what you could do is make a transaction that has as its max gas limit the total amount of gas with not one gas unit remaining. That could be the maximum allowed in a block for the next block. And if you make this huge transaction, you would guarantee that your transaction's the only one in the block, and therefore also the first one. So you'd have to maybe pay this insurmountable fee, and miners might not take it, but that's one way around it. That's the only exception that I know of. So if you can think of any other answer to this riddle, then let me know. Okay, so I'm going to wrap up with this rant part of it. What's the moral of the story here? There really isn't one. People use Turing completeness in Reddit posts, but it's not that meaningful. I don't see anyone making a really strong or well-received argument in favor of one thing or another based on this, and so it's kind of a nitpicky thing that I wanted to describe. Trying to make some moral of it, there is a kind of underlying trade-off here that's significant, which is that it's not just about Turing complete is dangerous and Turing incomplete is safe, but in general what we care about in designing programming languages is providing a combination of expressiveness, meaning it's easy and natural to write programs that you care about writing, and also transparency, meaning that it's easy to analyze them, or it's amenable to formal analysis, or it's amenable to human understanding. And these two are somewhat at odds with each other. It's not like a perfect trade-off, kind of in the same way that security and privacy aren't a trade-off that you have to switch between. You want both, and so the directions in programming language research, which are what I really advocate and what we work on a lot at IC3, are trying to improve on both the expressiveness and the transparency. And so that's the only meaningful trade-off that I think people might have in mind. And the words Turing completeness that they use maybe just are noise, but doesn't detract too much from the point. So let me pause here if you have any questions before I go on. So sure.
Isn't it a red herring only in that they're asking a programming language to do something that execution and operations typically guarantee, like asset transactions, like failovers, dealing with all the Murphy's Law things that can happen. And so to say that it's just about a programming language, in a sense, isn't really answering the question, because in your example for the jigsaw character,
Yeah.
couldn't somebody try and either compromise the EVM or compromise the jigsaw or his communication with the EVMs? So in a sense, you're trying to solve for something that I would say that the red herrings that you're trying to solve with the programming is something that requires something larger.
Sure, there's a meaningful debate there. So the Turing completeness part's a red herring anyway, but there is a meaningful debate about whether you should move the burden of maybe guaranteeing invariance or making it easy to use down to the machine level, like to have the virtual machine support all of this, versus up to the programming language level and having it control of that. So I know the DAO conversation was last time, and I don't have material on it, but that's also an interesting example. So you could say, well, here are all these weird behaviors of the virtual machine that get compromised in a language, so you could try to modify the virtual machine to just eradicate all these kinds of behavior, but you could also just move it up, and this is the approach that I think. I think the EVM is fine in this case. You could try to design things at higher level languages that allow you to get some guarantee that some invariants aren't violated, like this reentrancy hazard. And if you just choose to only interact with contracts that you know you can see this chain of provenance, they were compiled from a high-level language, and the high-level program has this property, I mean, I think that's adequate. But that is really the opposite of transparency, is like shoot yourself in the footedness. Like you in general want to make a system that's hard to make mistakes in. And so it's not Turing completeness. That's kind of the only depth that my rant goes into. But that's a meaningful trade-off, sure. Yeah.
You were saying before, the UTXO in Bitcoin is kind of constraining. You're spent or unspent. How much do you think about like the scalability of Ethereum's state? When you're designing these systems as opposed to Bitcoin, or just generally, is it a constraint that you think about?
Yeah, for sure. I don't have any super answer for that. Yeah, with Bitcoin, you don't have any way except for the UTXOs of putting values not just into the blockchain, which people can prune and forget about, but into the UTXO set, which is the live memory that might be accessed at any time that people need to keep track of. Just because you can only do it for payments with UTXOs doesn't mean that people aren't going to abuse it anyway. So I can fill up the UTXO set with non-monetary data, and unless they make fees more restrictive, they're not going to be able to keep me from doing that. And similarly in Ethereum, they try to add a fee penalty to make it expensive to do so, but you can't help people putting data in there. So I would say it depends more on usage than on the restriction. I don't think that there's a clear argument that the UTXO structure fixes scalability in the case of Bitcoin that you can't also have by being able to store arbitrary application state. Yeah?
Can you use Ethereum to develop an encrypted HIPAA-compliant system? Because there are obviously huge issues with hijacking data from hospitals now.
Yeah, I'm going to go on in just a second to the second part of my talk, which is totally going to be relevant to that. And if it doesn't directly answer your question, then I'll talk with you right after that. Okay, so having finished my rant, let me go on to talk about something more productive or constructive, I should say. So I'm going to tell you about this research project that a student at University of Maryland, Ahmed Kospa, and I, as well as other folks at Cornell and at UMD did, which is a framework for building privacy-preserving contracts on top of Ethereum. So back to the general purpose smart contract programming model. This is great. We can write arbitrary programs that run on the blockchain. That's awesome and really powerful. We should think of the blockchain as a sort of virtual trusted third party, but it's critically a trusted third party that guarantees availability and correctness, like it'll run your program correct and let you send input to it, but it doesn't make any sort of privacy guarantee. Everything you do on the blockchain here is public, right? And that poses some serious concerns. I'm sure you all know this, but I typically give a little intro slide about how well Ethereum's doing so far. So you can make arbitrary contracts, and so far there have been more than 7 million transactions, and there's almost 100,000 instances of these user programmed smart contracts running on the system. So this is great. It's a real-life system that people are already starting to use. If you follow the manual for programming interesting applications in Ethereum, they'll walk you through all sorts of examples, including an auction. But there's a big concern, which is that by default, anything that you put on this blockchain is public. So the code that you put is public. You can reconstruct it and figure out what the code does, even if you didn't think anyone was going to be able to. All the data you send to the contract that's application specific, you can see, and all the money to or from the contract's visible. All right, so depending on what kind of applications you're doing here, this can have meaningful privacy loss or not. So if you're investing in stocks via the blockchain, then it'll reveal what stocks you have an interest in. If you have some kind of insurance smart contract, then people can tell what risks you're worried about. And if you try to do something like an order book matching thing, then an attacker can front run your order because the attacker can see what's going on the blockchain network before a transaction's even committed in a block. So he can outrun your order and sneak one in front of you. And indeed, if you follow the standard tutorials for how to build an auction in Ethereum, you end up with something that leaks more information than you might want. So if you wanted to build a second price auction, a sealed second price auction, where everyone submits a bid and then the winner gets the second price and everyone else gets a refund, you would put the code for this on the blockchain, and here's what would happen. You would have some phase where all of the users send their bids, and when you send a bid, you send money to the blockchain contract. All right, and then once all of the bids are in, you reach some finalized phase, then it does the output. It calculates how much the winner should have to pay, and it gives everyone else the corresponding refund. Now the catch, though, is that when you submit your bid, from the moment any party submits their bid, the attacker gets to see what it is. And this in particular poses a hazard because the adversary can decide whether or not to collude by posting two bids at the same time towards the end of the contract in order to see if he wants to try to affect the outcome using this information that in a sealed bid auction you wouldn't have. So our approach to fix this is to develop this framework for privacy-preserving contracts. And the key idea here is that we're going to be using zero-knowledge proofs. So these are advanced moon math cryptography that allows you to prove statements about some ciphertext, about the plain text like concealed within a ciphertext, without revealing any more information about the plain text other than the fact you're trying to prove about it. We're going to be using the same underlying zero-knowledge proof scheme that was used in Zero Cash. So Zero Cash, as you may know, was a research paper also at Oakland a couple of years ago, and is now going to be released soon by the company Zcash, so it's going to be an altcoin. What we're trying to do is, right, and so Ethereum adds to Bitcoin this layer of programmability, whereas Zcash adds this layer of privacy. What we're trying to do with Hawk is try to add the best of both worlds. We wanted to allow you to have the expressive programmability of Ethereum while also allowing you to have privacy-preserving transactions with these smart contracts. Okay, so the best of both worlds is the goal of Hawk. So in a Hawk auction, it looks a little bit different. What we have on the blockchain is, instead of the code of the contract in plain language, what we have are the public parameters for one of these zero-knowledge proof schemes. That's kind of like a representation of the function in a couple of small crypto elements. And so what happens is that there are now one more phase. So in the first phase, users send not their bids in plain text, but a commitment of their bid. So a commitment's just an encryption with a random key R that allows you to reveal that key later, and then everyone can see what the output was. All right, so the users submit their commitments to their bids along with the zero-knowledge proof, which guarantees that they actually have the money that they're trying to spend and that they aren't double spending at this point. In a second phase, we're going to introduce this somewhat trusted third party called a manager, which I'll talk more about in a little bit. And so after all of the bids are in, what happens is the users reveal their bids to the manager by revealing to the manager the randomness that they use to make their encryption. All right, so the manager at this point is going to learn, after all of the bids have been committed to, the manager is going to learn what all of the bids are in plain text. And the final step is that the manager sends one final transaction to the contract, which is an encryption to each of the users of the refunds or the winning value that they're supposed to get according to the application, along with one final zero-knowledge proof, which says that the manager included all of the values, that the values are the correct ones that were committed to originally, and that he ran the application function correctly, and that all of these outputs are consistent with the output of that function. So I introduced this trusted third party, so you should immediately be totally skeptical and want to know details about it. So the only thing that I can do is to say exactly in what ways we're trusting this manager. So we don't have to trust the manager for correctness. He can't modify the function because he has to produce the zero-knowledge proof which says that it's computed correctly. We don't have to trust the manager for input independence, which is crypto jargon, but it basically means he can't front run. And this is what's achieved by having all of the commitments to the bids placed ahead of time before the manager learns what any of the inputs to the bids were. We don't have to trust the manager for the security or privacy of the underlying cryptocurrency. So this is built on top of the zero cash protocol, or a simplified version of the zero cash protocol. So there is a contract, but outside the contract you can also send and receive private payments. And so even if the manager goes completely bad, it doesn't affect your ability to transact with the underlying private currency. We don't have to trust the manager for fairness, because if the manager doesn't, what I mean by this is that the manager can't exclude some party's information and censor them, and he can't just walk away from the contract without penalty. And we do this by collecting a security deposit from the manager at the beginning of the contract. And so this gets paid out as compensation to the parties if the manager goes away and doesn't do that last part. The only thing you have to trust the manager for is posterior privacy. So he can't learn information that affects the contract, but he does learn all of the parties' private inputs by the end of the contract. All right, so he could leak them if he goes wrong. And the privacy guarantee of this scheme is that it isn't revealing the parties' inputs even after the fact to the public, only to one party that computes these final zero-knowledge proofs. All right, and the last caveat is that this manager is really a logical role. So in the performance experiment that I'm going to mention shortly, it's just run on a single computer. But you could also imagine implementing the manager on top of a multi-party computation or using trusted hardware, and this would give you more security guarantees even about this posterior privacy part. So we could have just made an auction, but we wanted to be more general and to carry the expressiveness of Ethereum, which was one of our goals. So instead of just having this application, we implemented a compiler that lets the user write an application in a simple language to describe what they want. And then the compiler's job is going to be able to generate this user-provided spec into a whole cryptographic protocol for all of the parties, and including a portion of a blockchain contract that implements that application. So for example, we implemented this framework, and then the particular example of a second price sealed bid auction is just expressed in about 20 lines of C code. So it's one function that's a mapping from the parties' inputs. The inputs can be an arbitrary string as well as some money, and then the outputs to each party can also be money or an arbitrary string. And the code just is simple, straightforward C code. It has a loop in the middle, and it loops over, it does what you would expect. So it's in an ordinary language that anyone can read if you know C. We also provided several other examples in the paper. So we similarly added one of these rock, paper, scissors games, like a 2-player lottery for money, as well as a crowdfund campaign where there's some threshold, and if you don't reach the threshold, everyone gets their money back. And if everyone gets their money back, no one knows how much money was donated, so you don't know, how far away from the goal you were. And also a really simple financial instrument that lets you bet on the price of a stock, assuming that you have some trusted signer who's going to be reporting the price of the stock. To give just a little bit detail about what the technical structure of this compile is, it's kind of like a Franken-Snark system, because we're using these several different components of existing zero-knowledge proof libraries. So the first part is that we take that user-friendly, user-provided C program, and we pass it as input to the Pinocchio compiler. So the Pinocchio is another project for zero-knowledge proofs that contains several parts, but one of the parts of Pinocchio is the C compiler to arithmetic circuits, and we use that. Arithmetic circuits are kind of like the native language for the zero-knowledge proof schemes that we use. So it takes a C program as a C function, and it turns it into an arithmetic circuit that matches that function. All right. The second step is that we have to build our crypto protocol around the user's function. So the user function is just a tiny part. Then we have all of these extra parts about making sure that the encryptions are correct, that the commitments are opened correctly, and that the total balance of the money is preserved by the function. And so to do that, we have to use, we end up using a more complicated circuit compositing library, which was developed by Ahmed. I thought I would have a link to this here, but there's a lot of work that goes into making encryption circuits like this, encryption functions, efficient when they're implemented as an arithmetic circuit. So normally crypto operations are tuned for your Intel processors and for a standard CPU. And here we're compiling it down to not assembly code, not to run on a CPU, but to run in one of these algebraic circuits. And so the whole challenge of finding efficient crypto routines and implementing them in an optimized way, we kind of have to do over again. And so Ahmed did a pretty systematic job of finding the best schemes that we could use and how to implement them efficiently here, and he built this library, JSnark, to build complicated circuits and stitch them together in this way. And so there'll be a link later, and you should check that out online if you're interested in building these. Then finally, once we have this big augmented arithmetic circuit, we pass it as input to libsnark libsnark, which is a open source library. It's the one that's used in zero cache. And this takes in arithmetic circuits as input, and then it can run the scheme overall. To describe so we implemented this, we made a benchmark experiment. Our benchmark had 100 users doing either the crowdfunding campaign or the auction. The performance was the same in either case. The most expensive step was for the zero knowledge proofs, and especially for the manager at the end, because he has to do a proof that depends on the inputs of all of the parties, so it grows linearly in the number of parties. And we got this down to taking 2.8 minutes to generate this proof. This is parallelized across 4 cores. Right, the goal of the users also have to prepare zero knowledge proof, but just one, and it doesn't depend on the number of other users that's there, and this took 40 seconds even just on a single core. Yeah?
Can you optimize it to use GPUs?
I believe that this could be optimized to be done on GPUs. I also think it could probably be optimized to be on ASICs as well, but I don't know of any that are like that.
GPUs.
You're trying to implement it?
Yeah.
That's awesome. I would love to hear more about that. You should try it on our circuits, and then we could compare directly. Does it take input from libsnark or from Pinocchio or any of these standard formats? Huh?
From Pinocchio.
It takes output from Pinocchio. That's the coolest thing ever. Okay, I'm going to talk with you right afterwards. That's great. Yeah, the main overhead for all of this is doing zero knowledge proofs. There is other cryptography, like doing the commitments, but it's kind of like negligible into comparison. So if you can speed the zero knowledge proving up by a GPU, that would give you the tremendous impact on this. What's also critical is the on-chain cost. So this is the part that everyone has to run. So on the blockchain, well, off the blockchain, people are creating these proofs, but on the blockchain, everyone just has to check the proofs. And the nice thing about the zero knowledge proof scheme that we use is that they're efficient to check. So the total on-chain cost for this whole experiment with 100 users and the final payout takes 1.5 seconds. So that's still a pretty beefy transaction to validate. It also takes 220K. So you know, a significant portion of a Bitcoin block, not too much in the Ethereum world. But anyway, this is the portion of the contract that everyone on the blockchain network has to run. There's a lot more information in our paper, so I'd encourage you to check out this link, oblivium.com/hawk, and you can see our paper. This JSNARK library for adding things to the output of Pinocchio and to build more efficient arithmetic circuits and to have other sorts of gadgets for encryption within a zero knowledge proof. You can see all of those tools already on JSNARK. Just as a word of like progress update, we're still working on releasing Hawk. The main bottleneck right now is that Ahmed has a more advanced version of his compiler that's even more optimized, and so he's waiting to finish that compiler and then rerun the Hawk experiment through this final optimizer again, and then we'll have the final version of Hawk available to download. So that'll come sometime soon. And then just to mention, so the Zero Cache team or a couple members of the Zero Cache team, as well as Ethereum engineers and Cornell students work together at the boot camp that I've mentioned several times now. And one of the goals, or one of the project that was successful, actually the project that won first prize, and so they got, I think, like 75 Ether or something to split among themselves, was to actually implement an opcode in Ethereum, like in a fork of Ethereum, that does the snark verification. So this is kind of the critical step to being able to enable all sorts of applications, including Hawk, but also including like Zero Cache in Ethereum was their example. So normally when I've given this talk before, I've said, and well, maybe we should do that. But so now we actually do have a fork of Ethereum, and there's code online for it that has a snark checking opcode in it, and that's super useful. So I'm really glad that was the outcome of that. So that's all. That's all for Hawk and for my rant at the beginning. I hope you liked it. And so please follow me on Twitter there if you don't already. So there you go. Enjoy a Hawk image. Thank you. Yeah.
What's the way, let's say from the first step, to the compiler, can you verify that code was actually compiled? And it's the output.
You mean?
Step 1 to 3.
Just to go to this.
You have the source code.
Yeah.
And after running it through the compiler, how can you verify that that was the stuff? That was the source code, and that's the outcome of the compiler?
You could run just these two steps. There's a good caveat, which I imagine is what you're getting at, which is that most zero-knowledge proof schemes, including the one that we use, require this complicated process to do setup. It's called in Bitcoin community the trusted setup problem. So we don't have any particularly great solution to that. It basically means that someone has to be creating a bunch of random numbers while generating the very final version of it's not for generating the circuit, but say once you have this circuit, part of what the libsnark backend does is it takes the circuit description, which anyone can look at, and someone has to go through this process where they generate random numbers, and then they end up with a tiny bit of information that you can put on the blockchain. But they need to throw those random numbers away, and if they don't throw the random numbers away, they could be used to create these false proofs. So what the Zcash team is doing, and is in another Oakland paper, and this is the best known way to go about this, is if you're really worried about that problem, you don't have anyone you're willing to trust to do the final setup phase, is you can do a multi-party computation with n parties, where if even one of the parties throws away their random numbers, then you can have confidence that the system as a whole is sound. But still there has to be that caveat, and we don't know any way around it. In practice, what this means is that you would have to go through one of these procedures for each new application that you want to build. So another good example might be to build a flexible contract that has a little interpreter in it, and then it takes some program code or some application-specific code as input. So you have one larger circuit that you can maybe reuse for multiple applications. But in general, to have a different circuit, you'll need to go through that setup phase again. Yeah, Arvind?
If you can have a clean slate redesign of the underlying cryptocurrency with that simplified life for is there some parts of this that you could push down to the cryptocurrency layer?
Not really. It might be useful to have opcodes. Like, so right now the Ethereum opcodes are all something, whatever, mod 256 bits, mod 2 to the 256. So those are its native instructions. That's actually not too bad, because we can implement like the exponentiation operation without too many steps, because there is an operation for mod a number that's not too much larger than that, and kind of the main operation that happens here is multiplication and addition mod some number that does fit within that range. So we can already use their high-level modular arithmetic. It would totally be better if we had opcodes to do the actual algebra group operations. Other than that, I can't really think of anything where the design of the Ethereum virtual machine has frustrated us, where it's like there's a clear thing to ask for. What ends up happening for checking this is that you just have to pack the verification key, which is that ZKP parameters thing that's on the blockchain, into some number of Ethereum words, but not too many. So the thing that we did in this boot camp was just add an opcode that does that check. So clearly just having that helps. I'm not sure what would...
Things like commitment and randomness and so on. We can chat later. I don't mean to mock the conversation.
Okay. Yeah, so the EVM also has some built-ins for, like, it has a built-in for ECDSA checking. It has a built-in for SHA-2 and SHA-3, but nothing else. So more opcodes helps. I don't have anything clear to say on that. Yeah.
Do you believe that there's an alliance that could, happen with Bitcoins later on in the future? And then also, as far as the government support, is there a possibility to create an alliance with the government over time to create, I guess, like a world-dominating currency that's virtual?
Maybe.
Maybe you guys are looking at.
I'm not looking at it. I wouldn't know where to start. That's so far out of my area. I don't have anything particularly useful to help with on that. It sounds plausible.
Bank of England.
The Rothschilds got to it 400 years ago.
Yeah.
Well, would you consider this a third wave organization? A third wave as far as, 2016 and beyond, one of the next paradigm shift companies?
I would consider a really large alliance that includes everything from cryptocurrencies to count as a third wave. That's probably all I have to offer.
So I don't know anything about how the zero knowledge proofs work, but it seems like a lot of computation. Why does it take 40 seconds on one CPU to generate, for one person to generate this?
It's a lot of cryptography computations. It's just like...
What kind of stuff is happening during that work?
There's two main phases. One of them is in parallel doing a bunch of crypto operations. So you have some representation of a math element. You have one of these for each wire in the circuit. And so you have to do some operation for each one of those, and each operation takes some chunk of time, kind of comparable to doing a signature. But then you have one of these for every gate in the circuit, and then the circuit's really large, like hundreds of thousands of gates. There's a second part which involves doing some Fourier transform thing, so just another math step, and it's not exactly all in parallel, but it can be done in parallel passes. So those are the two main phases of it. So ideally, we would implement both of those with help with the GPU. Where'd he go?
He'll be back.
He'll be back. He better be back. Okay. Yeah.
Yeah, sort of a related question to that. If you could speak a little about what the Pinocchio compiler does and what these circuits are that are the sort of the native machine language of libsnarks and ZK proofs.
So the circuits allow you to basically do two things. You can have a multiply gate and an addition gate. And all of these are multiplications and additions mod some 254-bit prime number. So you can't just necessarily treat them as like arbitrary integers, whatever, but they can also be about that large, almost like a 32-bit word size or 256-bit word size. So what the compiler does is it takes the C code, which has things like ifs and branching and memory and all of that, and it just basically unpacks it and unrolls all of the loops into one of these circuits where everything's expressed as just these multiplications and additions. And it's like you can have a multiplication gate with inputs from arbitrary other wires in the circuit, and each one of those wires can be scaled by some constant. And so there's like a little grab bag of tricks. Like if you want to do equality comparison, you have a wire that's fixed to 0, and then you have like 1 minus x times x has to be equal to 0, and then that only works if the number is 0 or 1. And there's like a couple of like kind of trick gadgets you can use. And so essentially the Pinocchio compiler has a list of gadgets for transforming C constructs into these, and then it just stitches everything together. That's my wavy example. Hope that's helpful in some way. Yeah, Bob?
Is the output of the compiler deterministic?
The output of the Pinocchio compiler is deterministic.
So if my concern is that if you throw a auction on the blockchain, you claim this auction is a second price auction, can I verify that the contract does what you say it does?
You have to go through the trusted setup procedure anyway, and so that would be a stumbling block that prevents you. If that's already been done, then yeah, sure.
Okay.
You can relegate that the compilation was done correctly, and so here's the simple mathematical statement. Here's what the setup procedure was supposed to output.
Still, there will be equivalent logic circuits, right?
Sure.
Okay.
You could. That's interesting. I wonder if you'd be able. You're asking like, if I compile the same code, am I going to have exactly the same thing?
I mean,
the circuits would be different. So doing the setup phase is not deterministic at all. So you would still have different outputs.
Well, but I mean, there are going to be multiple logic circuits. Different optimizations that are done by the compiler, for instance. And with smart contracts, I mean, when the DAO first came up, I looked at its smart contract, and I was terrified of the damn thing. There's no way I could convince myself that I knew what it did by reading its code.
Right.
It's huge. And so with these kind of smart contracts, one of the things the community needs to face is how do we convince people to send money to this random number?
Yeah.
It's just so weird. People need to be convinced that that's a safe thing to do, and it's going to do what they expect. So that's anyway going to be an issue. How do you prove that the place you're sending your money is what you think it is?
Yeah, absolutely. I mean, I should say at a high level, one of the goals for this is the goal of having correct by construction programming languages, where we want to move, like smart contracts have inevitable really complicated parts, and what we would like to do is move the specification of it to a very small, simple language. So I would claim that you can read this straight line C code and figure out pretty clearly what it does, because it's not that complex or convoluted. And actually what this is hiding, what is all the stuff that the hot compiler generates, which is like several rounds of protocols and lots of cryptography and stuff. And so rather than have to redo that for every application, we have one of those. Yeah, you would still have to look at our paper and understand our transformation, but we can prove that that's correct, at least on paper, and we could approach that with formal tools to show that we did it correctly too. And so the flexibility of it, though, comes from the specification language, and that's maybe a little smaller. So that's kind of the main programming language lever that we have to try to make the trusted computing base, so to speak, smaller. But yeah, that's a general concern, and this isn't a magic bullet in that way. Yeah. You just raise your hand. Okay, let's back down. Whatever. Yes?
I didn't follow exactly all of the setup. Could you say what is actually in TCP here? Not in this example, but in the compiler and the runtime, the libraries. What do you have to trust?
I mean, you have to trust all of it. The key thing is that if you trust the Hawk compiler in that process, which you can check because we have defined that, and you'll be able to look at that code and check it once, that covers a huge part of the complexity of all the different applications. You have to inspect that there aren't bugs in the code that we have. We don't have anything that that isn't a problem that you solve by just eliminating all code. The best that we can do is to try to provide levers where there's a small portion that varies per different applications, and it all makes use of the same generic implementation of the cryptography. And for sure what we would look towards doing as soon as we have resources to do so is mechanical verification of the Hawk cryptography and implementation. So this would mean that you would have an even smaller code base, so you would have to trust the formal proof checker, and you would have to trust our theorem statements, but that's still a whole lot simpler than the whole code. But we don't have that now, but that's the goal. Again, agree that the implementation of it does what you want it to is correct.
Right, so then it's only the proof checker.
Mm-hmm.
What else is left?
The security statements of Hawk. So we actually have a formal model for Hawk in the paper, which is typically only cryptographers are interested in looking at, but it might be relevant to explain. So in terms of our formalization, I don't have any slides for this here, but let me try to describe it. So in general, formalizing cryptography is a challenge. Typically it's done with these game-based definitions. So I say, like, here's an indistinguishability game, I don't want the attacker to win on it. Here's like a soundness breaking the game, we don't want the attacker to win at it. What we do in Hawk is use a more generic, what we think is the crypto framework of the future, which is based on simulation security. And so what we say is, here's code for a trusted third party, where if a trusted third party ran this code, you could look at the code as simple enough, you could look at it and understand that it would be doing its job. You would just have to trust the third party. But then that's our specification, and what we prove is that our crypto protocol and all its complication is just as good to use as if you were using a trusted third party, only with a trusted third party out of it. So if you don't understand that, it's like just...
How are the proofs performed?
On paper are our proofs. In the future, and we try to make progress on this, all proofs will be mechanically checkable. But ours isn't there yet.
How large is the proof?
In pages of LaTeX or in...
I mean, pick your unit.
It's about 8 pages.
Sorry?
It's about 8 pages of proof. Okay, thanks. Yeah, it isn't.
How optimistic are you about improvements in performance and the size of compacting these proofs and things like that? How optimistic are you?
I don't know much about compacting the size of the proofs. I haven't thought about that because this is kind of, what's enabled this is this big breakthrough in succinct zero-knowledge proofs. So that's already quite small. I'm totally optimistic about the potential of parallelizing and optimizing the proof generating process. Yeah.
I'm fairly new to this, and there's a lot of information. Would this PowerPoint and other resources I could read be available online for me to access?
Yeah, sure, absolutely. You can get to our paper link, and the slides for this can be put online.
All right, thank you.
Go to this website for Hawk. You can find our paper there. And I don't know, go to the meetup website later for these slides. Yeah.
Could you also tell us a little more about JSNARC and the sort of hand-wavy second compiler?
Sure. This is a library for putting together circuits. So instead of having C code, which still is kind of like higher level and abstract, this allows you to get, like, really write down to it and say, I need this many wires, or I can make little gadgets like a encryption gadget where the inputs of this are wires directly in the arithmetic circuit. So you can build more optimized things with this.
What goes in?
It's Java code, so it's kind of like a template library in Java. So you write Java code that describes the circuit, and then you can run this Java code either just in test mode where it outputs circuit values and it solves the circuit, or you can run it in prover mode where it generates the proofs.
And it was sufficient so that you were able to like have a Java source and out came the end?
Yeah. Sorry, you were saying the...
Yeah. In your previous example, you said that Turing wasn't expressive enough to sort of allow Alice to tell when Jigsaw...
Yeah. Oh, do you have an answer for that riddle? Right.
I wish, no, but that's actually like a kind of privacy where you are not able to tell until afterwards whether Jigsaw has like.
No, it's not that, because you can tell, because you can see, and like an attacker for sure can tell. The problem is you can't from the contract do anything that guarantees that it's there or not. In other words,
like you can't write a contract to win this game.
Right, exactly.
Yeah,
yes.
okay. I understand now.
So it's the worst of both. It's not strong privacy, but also, yeah, it frustrates you solving the game. Cool. Okay. Yeah.
If part of the idea of using the algorithmic circuits is to minimize the number of, or minimize the complexity and the number of parties you need to trust, what about simply skipping that and going directly from C to Intel microcode?
The goal of the circuits is just so that we can use the zero-knowledge proof scheme. And so the reason we use circuits is because that's the direct format that the math of the cryptography underlying that zero-knowledge proof scheme uses. So going to Intel microcode wouldn't help because we don't have a zero-knowledge proof scheme that operates on that kind of instruction set. Yeah?
If I'm a participant in the auction and all the bids are sealed and I'm putting trust in the manager, is there any way for me as like a participant to audit the result and ensure that what occurred as far as like the order of the manager is transparent or accurate, or is that a black box to me as
The oracle, so in the stock price example, the oracle can be audited after the fact because the oracle input can just be public information. You don't see what the manager does for its outputs to other parties, but if you trust the zero-knowledge proof scheme, so if this relies only on the cryptography, the fact that the manager does the zero-knowledge proof guarantees that he can't modify the function and change the outputs of the function. And again, nor can he see what the input bids were before all the commitments are collected.
All right, if that's all, let's thank Andrew again.
Thank you.
We've got to clear the room by 8:30, but some of us are going to head over to the Beer Authority across the street, and you're welcome to join us.
Second floor.
Second floor.
Beer Authority. Great job, thank you. Thanks, Bob.
Just had Suku here a few weeks ago telling us about well.
Really? Oh, cool. Perfect.
Hey, great speech. Killed it, man. How old are you?
29.
29. Where are you originally from?
Florida.
Okay, which part?
Orlando.
Tampa.
No way.
Yeah.
Tons of friends in Tampa. That's awesome.
Man. We're like neighbors.
That's
hey,
cool.
Well, best of luck, man. Do you have a card or anything?
Thanks so much. You can get me on my Twitter. That's better.
I got your Twitter. 1024.
Okay, that's all I have.
1024.
Yes, 1024.
1024.
Yeah.
Awesome. Y'all send you a message.
Sure.
And Bud.
Jesse. Pleasure to meet you too. Take care.
Andrew and Bud.
Hey, Bud. Good to meet you.